So, machine learning. You've heard this term thrown around everywhere, right? It sounds like something straight out of science fiction, but it's actually the technology that's running your search engine, filtering your spam emails, pretty much powering our digital lives. So what is it, really? Well, in this explainer, we're going to pull back the curtain and demystify it completely. So let's just dive right into the big question. How does a machine, a chunk of code on a computer, actually learn anything? It almost feels like it shouldn't be possible. But here's the secret. It's not magic. It's a really logical process that we can break down step by step. All right, first up, what is machine learning? Well, the subtitle here says it all, really. At its core, it is all about finding patterns in data. Okay, so here's the official definition, but I want you to focus on just two words here: automated and meaningful. Automated means the machine is doing the heavy lifting, finding patterns on its own, without a person having to write code for every single possible rule. And meaningful is just as important. The goal isn't to find some random, useless connection. It's to uncover patterns that are actually helpful for making predictions or smarter decisions. And look, this isn't some far-off future tech. It's literally all around you every single day. That search engine that just seems to read your mind, that's machine learning. Your email inbox that knows what's spam and what's not? Yep, that too. Your bank flagging a weird charge on your credit card? Machine learning. Even your phone's camera instantly finding faces in a group photo, or your smart speaker understanding what you just said, it's all powered by this exact same idea. Okay, but that kind of begs a question, right? If we humans are so smart, why do we even need machines to do this for us? I mean, why not just program in the rules ourselves? Well, it really boils down to two big reasons. First, there are things that we humans do incredibly well, but we have no idea how to explain the rules. Think about driving a car, or even just recognizing a friend's voice. You just do it. But could you write down a list of rules to teach a computer every single possibility? No way. It's just too complex. And then there's the other side of the coin, tasks that are just way beyond human scale. No single person or even a team of people could possibly read the entire internet to give you the best search result, or analyze the mountains of data coming from a telescope. For these kinds of problems, we need machines to do the learning. Okay, so to really get how this all works, let's forget the jargon for a second and use a simple story. We're going to call it the papaya problem. And trust me, it's a fantastic way to understand the core concepts without a single bit of complicated math. So I want you to imagine something. You're on this incredible Pacific island, surrounded by papaya trees. The problem is, you love eating papayas, but you're clueless. You have absolutely no idea how to tell a delicious sweet one from a bland, disappointing one. So what do? You start experimenting, right? You grab a papaya, you feel it. Is it hard? Is it soft? You look at the color, and then you take a bite, and you make a little mental note. Okay, that one was kind of yellow, a little soft, and it was delicious. Then you try another. This one was green, hard as a rock, and definitely not tasty. What you're doing, without even realizing it, is collecting what we call training data. Every single papaya is a new piece of information. And believe it or not, that little papaya experiment you just did, that is a perfect stand-in for how a machine actually learns. Welcome to the machine's classroom. It's a bit more formal, sure, but the fundamental idea is exactly the same. So, in this formal world, there are basically 4 key ingredients to learning. First, you have the domain. That's just a fancy way of saying all the possible papayas on the whole island. Next, you've got the labels. These are the answers you care about, so for us, it's a simple choice: tasty or not tasty. Third is the training data. That's your personal collection, the specific papayas you've already tasted and made notes on. And finally, the most important part is the learner's output. This is the big payoff. It's the rule you come up with. Like, if a papaya is mostly yellow and a little soft, then it's going to be tasty. Now, in the machine learning world, that final rule you've created has a special name: a hypothesis. But don't let that term intimidate you. Seriously, all it is a function. It's a rule that takes a brand new, unknown thing, like a papaya you're about to buy at the market, and it spits out a prediction: tasty or not tasty. That's it. Okay, hold on. You could probably come up with a bunch of different rules, right? Yellow and soft, or maybe orange and firm, or anything but green. So how does the machine figure out which one is actually the best one to use? It's actually pretty simple and kind of common sense. The machine just looks back at its own experience, at that training data. It's like it's checking its homework. It tries out all the possible rules on the papayas it already knows the answers for, and it picks the one that got it right the most often, the one that made the fewest mistakes. So if your yellow and soft rule worked for 9 out of 10 of the papayas you tried, Well, that's a pretty darn good rule. So now that we've got the basic idea down, it's cool to know that machines can learn in a few different styles. Our whole papaya problem? That's what we call learning with a teacher. The two main flavors you'll hear about are supervised and unsupervised learning. Supervised is exactly what we just did with the papayas. You had labeled data. You knew if each one was tasty or not tasty. It's like studying for a test when you have the answer key. The goal is clear. Learn from the answers to predict future ones. Now, unsupervised is a whole different ballgame. Imagine you just get a giant pile of papayas with no labels. Your job isn't to predict tasty, but to just find interesting patterns. Maybe you'd find they naturally clump into 3 groups: small green ones, big yellow ones, and medium orange ones. You're discovering the structure on your own without any answer key at all. But, and this is a big but, this whole process of finding the best rule, it's not always so easy. In fact, there's this fundamental challenge, this kind of tightrope walk, that's right at the very heart of all machine learning. Think back to your papaya rule for a second. You can make a really simple rule, like all hard papayas are bad. It's easy, but it's probably going to be wrong a lot of the time. But what if you go to the other extreme? You could create an insanely detailed rule that perfectly describes every single papaya you've ever eaten. The problem? That rule hasn't learned anything. It's just memorized the past. It'll be totally useless for a new papaya it's never seen before. See the problem? This is what we call the bias complexity trade-off. So this table here really lays it all out. On one side, you have your simple model. It makes big, broad assumptions. That's what we call bias. And it often gets things wrong. The fancy term for this is underfitting. On the other side, you have your super complex model. It fits your past data perfectly, but it's brittle and will fail on new data. That's called variance. And we call that overfitting. The entire game, the real art of machine learning, is finding that perfect sweet spot right in between. And all of this leads to a really profound, almost philosophical idea in this field. It's sometimes called the no free lunch theorem. And it all boils down to this one powerful sentence: there is no universal learner. So what does that actually mean for us? It means there's no silver bullet. There's no one-size-fits-all algorithm that's best for every problem in the universe. The algorithm you'd use to predict the weather is totally different from the one you'd use to find spam. And that's why the human expert, the data scientist, is still so crucial. It's their job to bring that prior knowledge to the table and choose the right tool for the right job. And that leaves us with one last, and maybe the most important question of all. Everything we've talked about, from spam filters to papayas, it all comes down to one thing: finding patterns in the data we give the machine. But what happens when the data we feed the machine is itself flawed? What if it's incomplete or biased or just plain wrong? That right there is the biggest challenge facing machine learning today. And it's something to really think about every time you use one of these incredibly powerful systems.